Well, good afternoon, everybody. First of all, thanks to you all for hanging around right until the end. And thanks very much to the organisers. I'm very pleased to be concluding the scientific part of what has been an absolutely fantastic conference. If I seem a little bit shaky, that's probably to do with the trance DJ that we were treated to that concluded the social parts of the conference. So I want to start my talk by coming clean with you all. When I'm referring to the first vertebral skeletal tissues, I am of course referring to the elements of conodonts. So if anyone was expecting more teethy or bony things, this is your opportunity to leave now. So I'll move on from there. So first of all then, what is the biomineralization toolkit? So the origin of biomineralization, mineralized skeletons, shells, teeth and bones is an absolutely integral part of the Ediacaran-Cambrian transition and the building of metazoan-dominated ecosystems. And integral to this is innovation in genome patterning that produced the ability of animals to build these mineralized skeletons. So this compilation that's now quite a few years old, I imagine is familiar to many of you in the room. So Gerwin and colleagues mapped out the origination of what I'm going to call the toolkit of messenger RNAs compared to the regulatory elements represented here by microRNAs in different metazoan phyla. So you can see that the toolkit, as it were, evolved in the deepest metazoan branches prior to, or predominantly, I should say, evolved in the deepest metazoan branches prior to the split between sponges and bilaterians, in comparison with microRNAs, the regulatory aspects that evolved after this split and predominantly within individual phyla. So this is this idea that there's this common inherited toolkit that is subsequently canalized by the addition of regulatory elements. So there's quite a lot of evidence that this plays a major role in the evolution of the skeleton. This is typified by this study from Dan Jackson and colleagues from in 2010. So they compared the nacre building gene sets in these two mollusks. So that's the pearl oyster and the abalone, as well as with the purple sea urchin, or more specifically the early embryonic skeletogenesis of this purple sea urchin. So they found that these two different mollusk groups independently evolved the ability to deposit nacre by comparing the transcriptome. There's very few similarities in the transcriptome of these two tissues. But crucially, that those genes that they did share, they also shared with the purple sea urchin. So they suggested that these ancestral genes were exapted into a biomineralization role, because we know the last common ancestor of the mollusks and the echinoderms, which we can argue about the date separately, but it must have been entirely soft-bodied, so it's independently acquired the ability to build a skeleton. So this is the so-called biomineralization toolkit hypothesis. And now this hypothesis has three predictions. So one would be that you have multiple independent origins of skeletal tissues. The other would be that you have this inherited organic scaffold and genetic framework that was inherited from a non-biomineralizing common ancestor. And finally, that you should see this repeated pattern of the increase in complexity associated with the increase in control from regulatory elements of the genome. So what can vertebrates add to this story? So this is a particularly fine example of a vertebrate, in case you weren't aware of what they are, from the Oxford Museum of Natural History. So if we compare the genes that control biomineralization in echinoderms and vertebrates, we see a similar pattern to that study from mollusks, in that you have an extensive common biomineralization toolkit between these two groups. And this is supported with the idea of the evolution of vertebrate skeletal tissues via the calcification of a cartilaginous skeleton. And this was recently strengthened by the discovery of a collagenous skeleton in this little guy, Amphioxus. So it's where is it? In here. So this is one of the nearest invertebrate chordate relatives of the vertebrates. So this is a suggestion that Amphioxus also inherited this organic skeleton from the common ancestor, although they don't biomineralize. So I wanted to see if we could test this idea using the fossil record, and in particular the fossil record of the oldest vertebrates that have biomineralized tissues. That's the conodonts. So conodonts are a group of extinct jawless fish. They first originate in the latest Cambrian, and they went all the way through the Paleozoic before their sad demise at the end of the Triassic. There's been considerable debate about their affinity, but most recent studies have placed them somewhere around the split between gnathostomes and cyclostomes, represented here by this polytomy. Okay. Now they come in two broad different groups. So they're entirely soft-bodied except for their phosphatic feeding elements, some of which have a single tissue. These are the so-called paraconodonts. So every time you see this little blue guy, I'm talking about a paraconodont. And then there are more complex elements that have these two distinct tissue types, or euconodonts, which dominate the vast majority of the conodont fossil record. So they have this unique tissue, the euconodont crown, represented here by this red tissue. So Jiping Dong and Phil and John Rapetsky examined the diversity of basal tissue structures in euconodonts, and they found that you essentially see the entire suite of diversity that you see in basically all euconodonts is found in the very earliest examples. So this represented here by this Proconodontus. Here we have this spheritic mineralization in the middle of the basal body. Then we have lamellar tissues in this part of the basal body, and then this is the crown tissue. And so I wanted to examine. Oops, sorry, I'm getting attached to something here. There we go. I'll move away. I wanted to examine a few more taxa. So these are all a range of lower order vision taxa, and we see a similar pattern whereby we see a diversity of different mineral strictures, but dominated by this pattern of spheritic mineralization in the middle of the basal body, and then lamellar tissue, and then crown tissue. So here's a zoomed in of a physical section image with EDX of this Bergstrom anathus, an early lower order vision euconodont. And if we have a look at an EDX map of carbon, so this very bright bit here over here is the resin. So you can see that the crown tissue has virtually no carbon in it at all, the hypermineralized crown. And then the basal body, the spheritic mineralized tissues here have got more carbon in than the lamellar tissue, but that in turn has more carbon than the crown tissue. So this is evidence perhaps for an inherited organic skeleton onto which conodont elements are built. We also know that these euconodont elements derive from paraconodont elements. So this is some work that I did with colleagues here in Bristol and elsewhere a few years ago. So I don't want to miss the video. So we used synchrotron tomography to examine the individual growth stages and demonstrated that this paraconodont element here grows in identical fashion to this euconodont element once you strip off that euconodont apomorphy, the crown. So we've got this pattern of the evolution of euconodonts from a grade of paraconodonts somewhere in the latest Cambrian, the latest Cambrian and the lowest order vision. So I wanted to examine the diversity of basal bodied tissues in not just the earliest euconodonts, but also in the complete elements of paraconodonts. So here are some typical simple morphologies of paraconodont elements, where you have a single tissue type here, shown here by this Furnishina, also in this Mullerodontus, and predominantly you've got growth on the basal part of the element only. Again, you see a similar pattern in another taxon here, Proneotodus. But in bigger and more complex elements, you see this apparent differentiation into two different tissues, because you have the growth of the tissue both on the base and up the sides. But we can add to that picture of complexity that even within closely related taxa that have apparently simple morphologies, we also see a more diversity of different tissue types. So this is ongoing work, but I'm starting to build up a repository of a range of different tissue types in these different paraconodonts. Here's another example of the similarity between this paraconodont here, Tundiconus, with the spheritic mineralization and lamellar tissue, very similar to Granatodontus here, with just with the addition of the euconodont crown. Similar story here with this example from the work of Jiping Dong and colleagues looking at this paraconodont, which is extremely similar to what we see in the condition with Proconodontus. Again, we've got lamellar tissue here and this spheritic mineralization. So there's this complex story of the acquisition of different mineralized tissues in the transition from paraconodonts to euconodonts, and I'm in the process of adding to the complexity of this, what's represented here. And this is very similar to what has been demonstrated by, amongst others, with Joe Keating and Phil Donahue, looking at the diversity of mineral structures in gnathostomes. So we see a similar pattern of the in different lineages, the acquisition of different complexity and a high diversity of tissue types and arrangements in the very earliest jawed vertebrates. And there's been a suggestion that this high diversity could be attributed to multiple duplication events of these secretory calcium-binding phosphoproteins, SCCP family of genes. So you get the high diversity of tissue forms is associated with the initial duplication, and then you get canalization because you're adding a regulatory element. So this would seem to conform to the pattern of multiple independent origins of mineralized tissues in the vertebrates. There's evidence for an inherited organic scaffold, an inherited genetic framework, and we see a pattern of increasing complexity and control. So this is something I'm going to pursue further by suggesting that this biomineralization toolkit is at work in many different animal groups, and the acquisition of mineralized skeletons at different parts and different lineages. So there's an awful lot of people that have contributed to this work in different ways, so I'd like to thank all of those. And if you'll give me another few seconds of your time, this is a bit of a heads up. The Geological Society is launching a brand new early career network, which is going to provide help and support for early career geoscientists in a whole range of different disciplines. This is going to be launching in February next year. I'm chairing the committee, so please watch this space for more information if you're interested in being involved in that network. So thank you very much for your attention.